Hello, ladies and gentlemen. Today's topic of my presentation is lightweight photoplethysmogram waveform change detection for resource-constrained IoT-enabled remote health monitoring devices. Myself, Shivaranjani PN, and my co-authors are M. Shabarimali Manigadan from the Department of Electrical Engineering, IIT Palakkad, India, and Lingareddy Sangaramandi from Information Communication Technology Department, University of Agder, Norway. In the introduction, I would like to introduce you to the photoplethysmogram signal, which is an inevitable part of almost all the health monitoring devices that is available today, including the pulse oximeter, which gained huge popularity during the COVID times. The PPG is a non-invasive optical technology to detect blood volume changes for heart rate monitoring. On the right, you can see a PPG signal with 3 cycles, and the blood volume changes are calculated based on the amount of detected light. The fiducial or the characteristic points of the PPG are marked here, which include the onset or the start of the PPG cycle, the systolic peak or the point of maximum cardiac output, the dicrotic notch, and the diastolic peak. The main features of the PPG include the crest time, that is the time period from the onset to the systolic peak, the decay time, that is the time period from the systolic peak to the next onset, and the PPI or the peak to pulse interval, which is the time period between consecutive systolic peak or consecutive onset. In this work, we use these fiducial points and features for accurately finding the wave for accurately finding the PPG waveform changes. There are many works in literature which talks about accurate detection of abnormal patterns of PPG and ECG. And in remote health monitoring applications and in home healthcare and remote patient monitoring, there is a need for accurately finding abnormalities and communication, where the communication has to be energy efficient, and the communication protocols should be designed in such a way that there is minimal energy consumption, and only those data which has to be transmitted, or only abnormal data has to be transmitted. There are many works proposed in literature by various researchers which talks about communication protocol and efficient and effective communication of abnormal PPG, abnormal patterns, abnormal waveform patterns from the point of view of ECG. While this area is not explored much from the point of view of PPG signals. From the rigorous literature review that we conducted, our inference was that there is a need to develop a reliable and energy efficient method for accurate detection of abnormal PPG patterns for remote health monitoring purposes. So the limitations of the existing method include the false alarms due to various artifacts and corrupted signal due to unavoidable circumstances like contact pressure, sensor movements, hand by body movements, ambient light interference, skin tone, etc. And obviously the energy consumption, limited battery capacity of IoT devices. So the major contribution from our side include that we are proposing a Fourier transform-based filtering approach for simultaneous suppression of baseline, power line, and high-frequency noises, and the estimation of pulse rate. We are also proposing a fast onset peak detection approach by using the first-order derivative and the negative zero crossing point. We are also proposing a waveform change detection using just 4 features, that is PPI, crest time, decay time, and systolic peak amplitude, with heuristic decision rules for waveform detecting waveform changes. And finally, we are also proposing a simple signal quality assessment method by using just the pulse rate and number of PPS detected. The figure shows the block diagram of the proposed PPG waveform change detection method. The main steps of this method include the pre-processing step, followed by the DFT-based filtering, which include the fast Fourier transform computation and the DFT-based noise removal and pulse rate estimation. In the next step, we have the derivative-based onset and peak detection, followed by the signal quality assessment using the pulse rate and the number of peaks detected from the previous step. Once once we have the acceptable PPG signals after the signal quality assessment, we are extracting the PPG parameters, which include the PPI, crest time, decay time, and the systolic peak amplitude. And then we are applying the PPG pattern change detection rules to classify the PPG patterns as pattern change or no pattern change. Once there is a pattern change that is detected, then the IoT communication protocol comes into picture. So let's explore each step in detail. The first step, which is the pre-processing step, includes the amplitude normalization, where we are normalizing the PPG signals into a uniform scale of -1 to 1. In the next step, we are finding the FFT, or we are computing the DFT using the fast Fourier transform approach. And together, in this step, we are also finding the pulse rate using the dominant spectral peak. That is, we are finding the pulse rate using the FFT and the dominant spectral peak that we can estimate from the FFT. On the right, we can see a PPG signal which is corrected by power line interference and baseline components. As you can see in figure B, which is the FFT spectrum of the signal in figure A, there is a peak at 50 Hz which corresponds to the power line interference, and there are peaks which happens in frequency less than 0.5 Hz. By using DFT filtering, we are setting the frequency components for all the frequency greater than 5 Hz and less than 0.5 Hz. That is, the useful frequency falls in the range of 0.5 to 5 Hz. So all the frequency components outside this range are set to 0. And the inverse Fourier transform is used for reconstructing the PPG signals after removal of the unwanted frequency components. In figure D, as you can see, the power line difference and the baseline wanted components have been removed, and we get a clean PPG signal. So this is discussed here. And in the fourth step, we have the signal quality assessment using only very three simple features. That is the pulse rate obtained from counting, or the pulse rate obtained by counting the number of peaks that is obtained by counting the number of systolic peaks, and the pulse rate obtained from the fast Fourier transform. Also, we are using the number of peaks also as a feature for the signal quality assessment. In this fifth step, we have the onset and systolic peak detection, where we are proposing a simple and fast systolic peak detection by using the derivative PPG. The derivative PPG is obtained by using the equation number 4, and the negative zero crossings of the derivative PPG are actually corresponding to the location of the systolic peak of the original signal. Once the systolic peaks are obtained, the onset can be very easily determined by finding the minimum point between two successive systolic peaks. Here you can find the algorithm of the proposed method, which include the first step, which is the signal quality assessment, where we are making sure that the number of peaks detected falls in a range from Pmin to Pmax, where the Pmin and Pmax are designated with respect to the maximum and the minimum number of peaks that can appear in the duration that we are taking. That is, the pulse rate can fall from the range from 30 to 300 beats per minute for normal human beings, which corresponds to 0.5 to 5 Hz. So depending on that number, we are making sure that the number of peaks that are detected falls in this range. And the next condition, we are also checking that the pulse rate that is estimated from the count-based method and the FFT spectrum do not differ more than 10. Which will be a criterion for classifying the signals as noisy and clean. In the next step, we are finding the parameters or the parameter extraction stage is happening, after which we are making sure that all the four features, that is systolic peak amplitude, rest time, decay time, and PPI of consecutive pulses do not vary by greater than 20%. That we are setting a threshold of 20%, and the variation of consecutive systolic peak amplitude, rest time, decay time, and PPI should not vary for more than 20%. Once this condition sticks, we are also making sure that the variation between the previous segment and this segment also do not vary. And if there is a variation that is found out, we are transmitting that PPG for further diagnostics. And if there is no variation that is detected, then it can be stored for future reference or it can be discarded. So this figure shows the various steps of the proposed PPG waveform change detection method. We have the original PPG signal in figure A, followed by the DFT filtered PPG signal. In figure C, we have the derivative PPG, and the zero crossing, negative zero crossing points are marked in red bubbles. In figure D, we have the systolic peak and the onset that is detected using our algorithm. In figure E, the output waveform is shown where the waveform change is detected. If there is a change in the systolic peak amplitude, PPI, crest time or decay time, then it indicates a 1, which indicates waveform changes. And if there are no changes between successive cycles, then it indicates a 0. So in the results and discussion, the evaluation database, we are using 4 standard database, which is widely used in literature. That is the Mimic, BIDMC, SLP, and REST PPG during exercise databases for test duration of 1 minute for our evaluation purpose. For comparison purpose, manual annotations of waveform changes are done using visual inspection. And the performance are evaluated using standard performance metrics like true positive, true negative, false positive, and false negative, and using metrics like sensitivity, specificity, and accuracy. And as I already mentioned, the decision rules are that if there are no parameter variation within cycles of the current clean segment and as compared to the cycle parameters of the past segment, then the current segment would not be stored or transmitted to the edge AI or cloud AI computing system. But if there is a variation in the cycle parameters for the current segment and past segment, then the current segment will be transmitted to the edge of cloud computing server for further analysis and diagnostics. These figures show the result for figure A, which is a clean PPG signal. There are no waveform changes detected. So the output indicates a red line of 0, which indicates there are no waveform changes. But in this case, when there is a change in systolic amplitude and PPI in this portion, our algorithm is clearly indicating that there is a waveform change in this portion and this portion. Due to changes in PPI, systolic peak amplitude, crest time or decay time. And coming to this case, when we can see a wide change in the amplitude, in the shape, in the PPI, etc. In this case also, our algorithm is showing that there is waveform change, but as you can see that there are inaccuracies in the accurate estimation. There are inaccuracy in the estimation of systolic peak and the position of the onset as shown in this figure due to the presence of visible dicrotic notch. That is, there is a visible presence of the dicrotic notch in this case, which is not actually visible in the previous 2 cases. So our method shows some problem in this kind of cases. Now coming to the tables, this table shows the performance of the proposed waveform change detection method for 3 databases, SLP, Mimic, and BIDMC, for 5 different records of each database. So we have the visual annotation results and the results of the algorithm, and the change between or the difference between these 2 methods that is determined in terms of the cycle changes and no cycle changes, and the difference between these 2 are found out to evaluate if the algorithm is performing well. Here the performance of the signal quality assessment approach is tested on the REST PPG database for 19 different records. And from this study, we found out that 13 records out of 19 records show 100% specificity, while 6 records show lesser specificities in correctly determining the noisy segments. Now, conclusion, in this study, we are presenting a simple and fast quality-aware PPG waveform pattern change detection method. And the event-triggered communication protocol can significantly reduce energy consumption by transmitting the PPG signal wirelessly only when the PPG signal exhibits morphological or rhythm variation in the present PPG segment as compared to the previous PPG segment. And the quality-aware waveform change detection method based data transmission protocol reduce energy consumption in continuous long-term PPG analysis with IoT-enabled edge and cloud AI computation systems. And the performance of the proposed method is evaluated using standard databases and performance metric with ground truth data obtained using visual inspection. In the future direction, we would like to implement the proposed method on resource-constrained computing platform for real-time energy consumption analysis with processing time using short-term and long-term PPG recordings. We would like to acknowledge the contribution of the Research Council of Norway for funding our research in the Indian Institute of Technology. Well, these are my references. Thank you.